This is the fifth section of the vectors chapter, and this is about finding points of intersection. So points of intersection between two lines, or a line and a plane. So easiest way to do it, the first thing to do is to write the vector equation of the line in column form. Okay, then once you've got them written in column form, and they will both have different scalars, so it may be lambda and mu, it might be s and t. Okay, we set them equal to each other, so you might have something like 3 plus 2 lambda, 5 plus lambda, negative lambda, so that might be one line, and what that came from would have been something like this: r equals 3, 5, 0 plus lambda 2, 1 minus 1. So can you see, basically you expand it out for one line, and then you make that equal to maybe the other line, so you might have 5 minus lambda, 6 plus 2 lambda, 5 lambda, and this would have come from, for example, a line, let's call this R2, which has this equation that may actually be written in IJK form, so it might be something like 5i plus 6j plus lambda. Actually, we need a different scalar here because it wouldn't be the same one. That wouldn't be nice. So let's change that to mu, for example. Did I have 5 mu at the bottom? Yeah, I did. And then it will be plus mu and then in brackets negative I plus 2k plus 2j plus 5k. Yeah, so these are what we would have started with at the bottom here, like something like that. We write them basically in this form, all in one vector. We set them equal to each other, and then the next step you can see in the next box is like solving them simultaneously, and you solve the first two equations simultaneously. Now there may not be any solutions. If there's no solutions, it means that the lines do not exist. If you solve the first two simultaneous equations and there is a solution, okay, you need to make sure that that solution satisfies the third equation. If it does, it means the lines do intersect, and then we can substitute in our value of lambda and mu to find out what the point of intersection is. And it's often useful to use the other equation that we have to check. So let's try one and see what happens. So the lines L1 and L2 have vector equations which are here, like this, respectively. Show that the two lines intersect, find the position of the point of intersection. So step number one, what we're going to do is we are going to write them in column form. So 3, 1, 1 plus lambda 1, negative 2, negative 1 for that line, and then the other line in column form. So that will be 0, negative 2, 3. So that's because there's no I part to the second one. So this is basically this one. This is basically this one, plus mu, and a negative 5, 1, 4. So what we do is basically put this and this into one bracket. So if I do that, I will get 3 plus lambda in the top line, 1 minus 2 lambda on the second line, and then 1 minus lambda on the third line. Okay, I'm going to set that equal to and we're making it equal to each other because we want to see if they intersect. And then what we'll have here is I'll actually write 0 minus 5 mu, and then negative 2 plus mu, and then 3 plus 4 mu. Okay, so that came from this. So we'll take the top two rows. So we'll take this row here, and we'll take this row here, and we're going to solve those two simultaneously and see if we get a solution. So we'll have 3 plus lambda equals negative 5 mu, and the second equation 1 minus 2 lambda equals minus 2 plus mu. Okay, now what I'm going to do, I'm going to make mu the subject of this second equation and substitute it into the first. So that will give me mu equals, so basically add 2 to both sides. So I'll get 3 minus 2 lambda. I'm now going to substitute that into this equation here. So if I do that, I'll get 3 plus lambda equals negative 5 mu, which is 3 minus 2 lambda. So 3 plus lambda equals negative 15 plus 10 lambda. Then I will take lambda away from both sides, so 3 equals negative 15 plus 9 lambda. Add 15 to both sides, so I'll have 9 lambda equals 18, which means lambda equals 2. Okay, so let's substitute that back in to the first equation, and I'll do that over here. So if I substitute that in to this equation here, that will give me 3 plus 2 equals negative 5 mu, okay, which means that mu equals negative 1. Now we need to check that works in the third equation, because we haven't used this equation here, the one I'm highlighting in blue. We haven't used that. We've got to check that it works in that equation. So now I'm going to substitute lambda equals 2 and mu equals negative 1 into that. So I'll have from this equation here 1 minus lambda, which is 2, equals 3 plus 4 times by negative 1, and we need to see if that works. So 1 minus 2 is negative 1, and then 3 minus 4 is negative 1, so it works in the third equation. So now we can work out what the point of intersection is by substituting the value of mu and lambda in. So I am going to substitute that into the first equation. Yeah, so R equals 311 plus lambda, lambda's 2, 1, negative 2, negative 1. So that will give me 3 plus 2, which is 5, 1 minus 4, which is negative 3, and 1 minus 2, which is negative 1. So this is the point of intersection, is 5, negative 3, negative 1. Now as a check, let me see if I get the same point if I substitute it into the second equation. So that would be 0, negative 2, 3, plus mu, which is negative 1, lots of negative 5, 1, 4. So I wouldn't necessarily need to do this, but it's useful as a check. Should get the same point. So I get 0 plus 5, I get negative 2 minus 1, and then I get 3 minus 4, so I get the same point. That's just a useful check. So here's my final answer, that the point of intersection is the point 5, negative 3, negative 1. So here we want to find the points of intersection between the line and the plane, and this is the equation of the line here, and this is the equation of the plane. Now you'll notice that they've both got r in, r equals an r dot. So to find the point of intersection, if they do intersect, then we need to equate the r's. Okay, so equate r, which basically means that we're going to substitute that r into here. Now before we do that, we need to write the equation, or write r equal to, we'll write it in column form, -1, 1, -5, plus, so we're sort of expanding our brackets, lambda, plus lambda, because it's like 1, 1, or 1i, plus 1j, plus 2k, so plus 2 lambda. So there's the line given as r. And then for the plane, r is just going to be r dot. So in column form, 1, 2, 3 equals 4. So now what we do, this we substitute into here. So this is going to give us -1 plus lambda, 1 plus lambda, -5 plus 2 lambda, dot 1, 2, 3 equals 4. So now we work out the dot product, and that's going to be equal to 4. So if you do the dot product, so that's going to give us -1 plus lambda times by 1 plus 1 plus lambda, 1 plus lambda times by 2 plus -5 plus 2 lambda times by 3 equals 4. So it's just a matter of solving this equation. So here we only have one parameter, only one scalar to solve the equation, which is it's much easier than doing two lines. So that's -1 plus lambda plus 2 lambda, so I'm just expanding the brackets, minus 15 plus 6 lambda equals 4. So what have I got? I've got a lambda, I've got 2 lambdas, 6 there, so I've got 7 lambda. And if I look at my numbers, -1 plus 2 minus 15. So I'll just correct that. Just realised I can't add. Lambda plus 2 lambda plus 6 lambda is 9 lambda. And then -1 plus 2 is 1, minus 15 is -14 equals 4. So add 14 to both sides, 9 lambda equals 18, that's nice, which means that lambda equals 2. So now that we've got lambda, if we want to find a point of intersection, that gets substituted into, and it has to be the equation of the line. We haven't got anything to substitute into the equation of the plane. So substituting that into the equation of the line, and let's do that up here. So let's put lots of arrows in so you know where I'm going here. So this point of intersection is going to be -1. Now lambda is 2, so plus 2. So this comes from here. Yeah, that is where we're substituting the lambda equals 2 into. So -1 plus 2, 1 plus 2, -5 plus 2. So hopefully I'll get my maths right. So -1 plus 2 is 1. 1 plus 2 is 3. -5 plus 2 is -3. So we have the point of intersection. Let's write this down. Point of intersection is 1, 3, -3. Now you could write this as a coordinate, 1, 3, -3, or you could write it as ijk, so I plus 3j minus 3k. So either one of these is fine. Oh, it does say coordinates at the point of intersection. It does say the word coordinates here. So actually I could leave it in either of the first two forms. Yeah, but really that's a coordinate there. 1, 3, -3. Okay, the lines L1 and L2 have those equations. Okay. Respectively, prove that L1 and L2 are skew. Now, lines are skew. Lines are skew if they are, so they need to have two features, not parallel. Okay, so they don't have the same or multiple direction vector, so not parallel, so we need to be looking at the direction vector to determine that, and they do not intersect, so do not intersect. So we need to show two things. So finding out whether they intersect is about solving, isn't it? Solving simultaneously and showing that there's no solution. So yeah, skew means that they are not parallel and they do not intersect. So we need to do that with these two lines. Now the first thing that we need to do is write them in like column form, equation form, because in Cartesian form it's going to be tricky to do. Right, so it's going to require us to remember a bit of information, and that's this, that if the equation of a line is written in Cartesian form like this, so x1 minus a1, or x minus a1 over b1 equals y minus a2 over b2 equals z minus a3 over b3. Now that's b2, not b squared. Then in scalar or vector form, it's r equals a1, a2, a3 plus lambda b1, b2, b3. So you'll need to remember that. I'm not sure if that's in the formula book or not. So converting L1 into that form, so the equation for L1 is going to be R equals, so A1, B1, sorry, A1, A2, A3 is going to be 2, so we need to watch out for the signs, -3 and 1 plus lambda, and then the way that we get the direction vector is the numbers at the bottom there, so that's 4, 2 and 1, because it's like z1 over 1 basically. And then for L2, that equation, so we'll do the same thing again. We want A1, A2, A3, so that's going to be -1, 0, 4, again watch out for the signs, plus, now it's a different line, so we shouldn't be using lambda again, so let's use mu, and then the direction vector is going to be 5, 4, minus 2. So let's set these up as equations and see how we go in terms of solving. This is a time when we actually don't want a solution. So starting with the top row, we'll equate these to each other. So 2 plus 4 lambda equals -1 plus 5 mu. Second row, -3 plus 2 lambda equals, well, that's going to be 0 plus 4 mu. And in the bottom row, 1 plus lambda equals 4 minus 2 mu. Now we want to make things easy for ourselves, so I'm going to rearrange this to make lambda the subject, which means taking 1 away from both sides. I'll have lambda equals 3 minus 2 mu. So I will take this and substitute that into, let's put it into this equation, the one that looks the next easiest. Yeah, and that will give me minus 3 plus 2 lambda, so lambda is now 3 minus 2 mu equals 4 mu. So from there we'll have negative 3 plus 6 minus 4 mu equals 4 mu. So from there I will have 8 mu equals, because I'm adding 4 to both sides, negative 3 plus 6 equals 3, which will give mu equals 3 over 8. Okay, so now let's take that and let's plug it into back into the first equation. So if that goes into here, I can then use that to work out what lambda is. So 1 plus lambda equals 4 minus 2 mu. Mu is now 3 over 8. So that gives me a value of lambda of, let's do this on a calculator, that'll be 17 over 4. Now, we've used the second two equations. I need to show that this doesn't work in the first equation. So if we call these equations 1, 2 and 3, we'll now sub what we've just worked out, our mu and lambda, into equation 1. And we don't want this to work. Let's see what happens. 2 plus 4 times lambda, which is now 17 over 4. Now does that equal negative 1 plus 5 times mu, which is 3/8? Let's see. So 4 times 17 over 4 is 17, plus 2 is 19, so I get 19 on this side. Okay, what do I get on the other side? I don't think that's 19. Negative 1 plus 5 times by 3/8. That is 7 over 8. Okay, they are not equal. And so we've done this bit here. We've shown that they do not intersect. By solving simultaneously, we don't have a solution that satisfies all three. And now, how about the other bit about them being parallel, not parallel? Well, let's have a look at the direction vectors. Right, they are not multiples of each other, so they are not parallel. Yeah, so now let's finish this question off by writing down our conclusion. Okay, so lines L1 and L2 are skew since, well, they do not intersect. They do not intersect, and we've shown that algebraically there's not a value of mu and lambda that satisfies all three, and their direction vectors, they're the bits that I've highlighted in green, are non-parallel. Yeah, so that's how we can show that lines are skew when they're not parallel and they do not intersect. So they pass each other without actually cutting through each other. Okay, you should now be able to do exercise 9E on pages 191 to 192. So just as a reminder, if you want to find lines that intersect, so intersecting lines, okay, we basically want to, if you've got a line like this, right, we want to write the equation in this form. Let's say A is A1, A2, A3, and B is this vector B1, B2, B3. Then we'd write the equation of this line as A1 plus lambda B1, A2 plus lambda B2, A3 plus lambda B3. We do the same for the second line, and then we're going to make them equal to one another. Okay, so this is going to be equal to however we write the other line. So let's call this C1, C2, C3 plus mu. Guess what letter we're going to use? D. D1, D2, D3. So here's our other line. And then once we've made them equal to each other, we solve two of the equations. Solve two equations, and then we need to check it works in the third. Check with third equation. Okay, and then from there we will actually be able to find mu and lambda, and then we substitute those back in to find the point of intersection. So sub back in lambda and mu to find point of intersection. If I want to find the intersection between a line and a plane, so if I put it intersecting lines and planes, this is easier because we'll have the equation of our line as r equals a plus lambda b, the equation of our plane as r dot n equals a dot n. That will be some sort of number on this side here. This will be like a constant. Then we just set them equal to each other. Or actually what we do is this bit gets substituted here, and then we solve like before, find lambda, substitute that back in to find the point of intersection, and the last thing is that skew lines do not intersect and are not parallel. So we can use the direction vectors to show that they're not parallel, and we can try and solve simultaneously and show that they don't intersect.